we have covered the fundamentals of biological reactions. Now, we move forward to the theories of suspended growth reactors. The kinetics and stoichiometry that is related to the energetics can be used to describe the rate of biological reactions, which can be incorporated into reactor mass balance and help us determine the reactor performance for wastewater treatment or resource recovery. The reactor mass balance for a certain compound or biomass can be written as the accumulation of said compound equals to the difference between the input and output plus the generation or minus the degradation through bioreactions. The reaction term, of course, is related to the kinetics and stoichiometry of that compound. Reactor configuration also plays an important role in influencing the reaction term. As I mentioned in the previous class, there are three major types of suspended growth reactors: CSTR, PFR, and batch reactors. Let's first recap the continuous stir tank reactors, or CSTR. It is continuously fed and vacated, and the liquid is well mixed in the reactor, forming homogeneous substrate and biomass mixture. This means the effluent quality is the same as the bulk solution quality in the reactor. The concentration of a generic component A is represented by Ca. Ca0 is the concentration of component A in the influent. Ca is the concentration of component A in the reactor bulk solution and in the effluent. So we can write the mass balance for CSTR. V times dCA over dt is the accumulation rate of component A in the reactor. It equals to FCA0, the mass of component A gets in the reactor per time, minus FCA, the mass of component A gets out of reactor, plus RA times V, which is the total reaction in the reactor. The reaction rate RA is determined by the stoichiometry and kinetics of component A in different processes. At steady state, there's no concentration change of component A, so dCA over dt equals 0. Then the mass balance equation becomes this. We can rearrange the mass balance equation so that the reactor volume can be calculated from reaction rate, flow rate, influent, and effluent concentrations. Switch RA and V can get this expression. V over F is the hydraulic retention time tau. Because there's no solid-liquid separation, HRT equals to SRT, which can be determined by the reaction rate and the concentration difference. In plug flow reactors, the reaction occurs along the reactor. The concentration of component A changes through the reactor. At the very beginning of the reactor, the component A concentration equals to influent concentration Ca0, while at the end of the reactor, the component A concentration equals to the effluent concentration CAF. To calculate the component A concentration at any location of the reactor, we can take a differential element at that location and consider it as a small CSTR, and conduct the mass balance. At the differential element delta x, the difference between the influent concentration CAX and the effluent concentration CAX plus delta x is the result of a reaction within delta x. Delta V is the product of delta x and the cross-sectional area A. We can divide both sides of the equation by delta x to get this differential equation that can be used to calculate component A concentration at a given time and location in the reactor. At steady state, where there is no change of concentration over time, Ca is related to the location x and the reaction rate R. After rearranging, we can express the reaction rate with this equation. Again, the reaction rate can be determined with stoichiometry and kinetics of component A. We can take the derivative for the steady state equation with dx on the left side and dCA on the right side. The left side becomes V over F, which is HRT, so we can calculate the reactor volume, or HRT, from the reaction rate and the integration of concentrations. The batch reactor is well mixed. The reaction occurs without feed or effluent, making this mass balance very simple. The accumulation just equals to the reaction rate, which is determined by stoichiometry and kinetics. In real life, we're dealing with non-ideal reactors. The mixing for the CSTR can be incomplete, or there can be axial mixing in PFR. Therefore, the residence time is not a constant but follows a distribution. For example, in a CSTR, a part of the component goes directly from the inlet to outlet for a shortcut, while some stay in the reactor much longer than most of the components. We can use inert tracer test to determine the residence time distribution by spiking certain amount of tracer and observe the tracer concentration in the effluent. Because the non-ideal reactor is a crossover between CSTR and PFR, we can model the non-ideal reactors with either CSTR in series method or PFR axial dispersion model. The more CSTR tanks there are in series, the more the system will perform like a PFR. An ideal PFR is essentially infinite amount of CSTR in series. On the other hand, the more axial mixing there is in PFR, the more it will perform like a CSTR. CSTR is essentially PFR with complete axial mixing. This figure shows the inert tracer concentration in the influent over time if a constant amount of tracer is added in the feed in the CSTR in series model. If there's only one tank, it is a perfect CSTR that is completely mixed, and the tracer is instantly diluted. Its concentration starts to accumulate as it is steadily fed and there's no reaction. The more tanks there are in series, more sudden the tracer will appear in the effluent, which is more like a PFR in which there's no mixing and dilution of the tracer. If the tracer is added at one spike instead of in a constant stream, the figure on the right shows the tracer profile in effluent over time. Can you think about why the tracer profile will look like this? The axial dispersion model adds a dispersion term to the ideal PFR model. The dispersion term is similar to Fick's law expression that describes diffusion. dL is the axial dispersion coefficient. The higher it is, more axial mixing there is. After scaling and transforming, the length and the time have been converted to unitless variables. The degree of dispersion is described by dL over VL, where V is the flow velocity and L is the reactor length. When dL over VL is 0, there's no dispersion in the reactor, so the reactor is an ideal PFR. But when the dL over VL is 1, there is complete dispersion. The reactor is an ideal CSTR.